Okay, let's get started. Hi, everyone. Um, this chapter we will discuss about the unsymmetrical fault analysis, right? We have learned from the previous chapter about the symmetrical component, right? And so you see that in last lecture we talked about symmetrical component. Okay, let me recap a little bit, right? The symmetrical component is the tool that we use to transform any unbalanced, right, voltage or current phasor. Okay, this is the tool that we use to transform and balance voltage or current phasors into the set of three sets, I would say, uh, three sets of balance. Okay, either V or I phasors. Okay, so it's a tool that to transform the unbalanced operation into balanced operation. This is normally done when to any kind of circuit, right? It can be done to any kind of electrical circuits, right? Which operates in unbalanced condition, right? It's not just in power system. Okay, um, we we're going to see, right, how to analyze the unsymmetrical types of fault, which is which will result in unbalanced voltage and current phases, right? As you can see that this kind of unsymmetrical fault, I mean, mostly happen in power system from the statistics. Okay, you can see that symmetrical fault, right, is the most severe short circuit, right? But it rarely happens. Okay, it rarely happens. But for unsymmetrical fault, the probability of occurrence is more than symmetrical fault. So we have to, be able to handle, right? We have to be able to calculate the unsymmetrical short circuit current, okay, or fault current, short circuit current, right? This is the our objective. We want to find the short circuit current. So these are the steps, the steps number 1 to 7, right? These are the steps how to analyze different types of faults. So we start from the first one on the flow chart, that the power system is under the occurrence of unbalanced faults. Then having this, power system operating in unbalanced condition, you apply the symmetrical component to transform, right, the ABC phase variables, right? The variables could be V or I. Okay, the variables can be either voltage or current. Okay, we transform this into the sequence variables, right? The reason behind this, is to transform the unbalanced condition in ABC to balanced condition in 0, 1, 2, right, sequence. Having this, after the transformation, you could have, three different kinds of networks depending upon the type of the fault we are discussing. Okay, we derive for the positive sequence network, negative sequence network, zero sequence network. Okay, then we find the Thevenin equivalence for each of these the sequence networks. Okay, and we connect all the Thevenin equivalence network for different types of fault. So basically, we are going to see three types of fault. Okay, we are going to analyze the three types of unsymmetrical, okay, faults. Still remember, what do we have? Single line to ground, right? Single line to ground, double line to ground, and you have double line fault, right? Line to line fault, or short circuit between any two lines, right? We have three types basically, right? This is single line to ground, double line to ground, and double line between line to line, okay? And soon after you connect this Thevenin equivalence network, then you can find the sequence, right, current and and sequence voltage for any points in power system. Then we since the sequence quantities, right, are not of our interest, right? We are not interested in sequence current or sequence currents or sequence voltage, right? So you have to transform this sequence current and the sequence voltage back to the original or to the phase ABC variables, right? So this is the final solution. The final solution would be, in the answer must be in ABC phase quantities, right? So these are the steps. So we will look into the findings in each of these types of faults. Okay, so we start by looking at this chart, right? This is a typical three-phase power system. Okay, this is the network, right? This is the network, and we are looking at the port A, B, and C, right? We have the current flowing. So the notation of this, we see this is a network, and this is the just like it's just like the load. So we follow the passive sign convention. Okay, we follow the passive sign convention. We see like this is the port that we are going to connect our load. Okay, so that's why the current is flowing into the positive polarity in this case. So it's going into the positive polarity. Okay, this is the general, or this is the original three-phase system, three-bus system, right? Three-phase bus system, right? Then we have to analyze the zero from the steps on the flow chart, right? The step number three, we're gonna write the zero sequence, positive sequence, and the negative sequence in this fashion, right? We're gonna write this part depending upon different types of faults, and then zero sequence. If you still remember, we have just zero. I mean zero sequence impedance, okay, and the sign convention for this, right? We also follow the passive sign convention, meaning that the current is flowing into the positive polarity. So you can see that this is a definition, right? That the I0, I1, and I2 is going out of the port, out of these two ports, okay. Now, this is the network. Okay, if you draw in terms of the equivalent circuit, right, at the fault terminal, okay, you can see that this is the equivalent circuit. We have the fault voltage at uh, only at positive sequence network, okay, whereby the other two sequence doesn't have any positive, I mean the voltage source, right? You can see that if you're going to write down the VI characteristics for this VI equation, right? You can see that if the current is flowing in this way, so it would create the positive polarity on this side and negative on this side, okay, and the voltage drop across C0 is C0 times I0, okay. You can see that here from this network itself, okay, the V0, the V naught here is in the opposite direction to this voltage drop. So you can see that the V0 here would be negative of I0 times C0. Okay, this is the from this circuit. So that's why when you write this equation, you see V0 is negative C0 times I0. Okay, so this is how you see the systems, right? Now we have the polarity in this form. You have the current I1 flowing from left to right, so that creates the voltage drop across the Z1 equal to I1 times Z1, right? So you KVL around this loop, so you get the second equation, okay, which is V1 is equal to Vf minus I1 Z1, right? This is just the normal voltage drops. So similarly, you see I2 flowing in this way, so this create the polarity, positive polarity on the left and negative polarity on the right, right? And the voltage drop across this is what? Is Z2, right, times I2, okay? C2 times I2. So the voltage V2 is in the opposite direction to this this voltage from C to I2. So this would be the negative sign, right? So V2 is equal to negative C to I2. So this is the equation, right? This is the general equation, right? Then we have to analyze what the Thevenin equivalence sequence network as we viewed it from the fault bus. Okay, now we analyze this example 9.1. Okay, this example 9.1 is we will go through this example. Okay, the power system sequence network and their Thevenin equivalent. So we're gonna trying to derive the sequence network for this particular power system, and also we're trying to find the equivalence, Thevenin equivalence for that. So the problem says that a single line diagram of three-phase power system is depicted in this picture, okay? And the negative sequence, negative and zero sequence reactance are also given. So you see that the zero sequence and positive sequence are given. You can see that the generator have different reactances from this is from the theory we learned, right? The reactance of each of these sequence network are different, right? Since we are dealing with the short circuit analysis, so the time frame that we are interested in is in the subtraction period, right? That means that it's just right after the fault. So this is it for the generator. For the motor, I suppose we would have something similar, right? So we see that for the machine, right, for the motor, we have the X double prime, which is subtraction reactance. We have X0, X2, right? Moreover, we connect this the neutral, right, to but not directly to. It's not solidly ground. Okay. In this case, for the generator, we call solidly grounded. Solidly grounded means that the neutral impedance is zero. Okay, it's connected directly to the ground. But in this case, right, the neutral of this motor is not solidly ground, but it's through the reactance of 5%, right? So the power system is given, and the parameters, both negative and zero sequence, are given. The neutral of generator, okay, and the delta and Y transformer are solidly grounded. The Y transformer are all solidly grounded, okay, and the neutral of the motor is grounded through the reactance and based on the motor base, okay. So the problem asks you to first to draw the per unit zero, positive, and negative sequence network. So we need to analyze the Thevenin, right? You need to find the Thevenin equivalence for zero sequence, positive sequence, and negative sequence based on 100 MVA 13.8 kV. Okay, so it's clear, right? There is no need to change any per unit quantity because you can see that the common base is the same as the machine itself, okay, and the voltage level of the machine is similar to the voltage of the primary of the transformers, right? So now you can see, right, this is 13.8, and the primary I mean the secondary voltage of this delta transformer, the transformer T2 is also the same as 13.8 over here. So there is no need to change for the per unit value. So we just take the value as given. Okay, this is clear, right? If we were to have different kV base, right? For example, here if it is 12 kV, you need to you need to convert this all these figures, right, to be in the same as the common MVA or KV, MVA and KV base, common system base. Okay, so now you see, then this is a problem to draw the per unit zero, negative, and positive sequence to reduce the network to Thevenin equivalence as viewed from bus 2. So I suppose that the fault is going to happen at bus 2. Okay, and the pre-fault voltage of the is VF is 1.05 and angle of 0, and pre-fault load current and the delta y phase shifting are neglected. Okay, you have seen from other example already that the pre-fault load current is normally negligible, right? It's normally negligible. Okay, it's normally negligible because it's just too small. It's just smaller than the fault current. And for simplicity, we normally, neglect the phase shifting, right? Now you see that if you have a different connection on primary and secondary, there is a phase shift of 30 degrees. So in this case, those phase shifts are neglected. Okay. So the first step, you see that how do we derive for the sequence network and the Thevenin equivalence is to to draw the picture, right? So now you can see that the big problem for drawing this sequence network is that we have to deal with different connection of delta and y, right? So this the flow of the neutral current or will be reflected, right, in the zero sequence. Now you see, okay, the zero sequence in this case, right, since the y of the generator, okay, the generator is y connected and is solely ground, so the reactance, right, the subtraction the reactance of zero sequence reactant. Sorry, this is zero sequence. The you deal with the zero sequence network. So at this point, okay, the zero sequence reactant is connected to ground because it is the solitary ground, right? So in this case, okay, it is delta in this case. So the delta is here, right? Um, so as you can see, right, the x of I mean x of this transformer, right? It is on the we normally assume that is on the primary side, and it is delta connected, so it is it is created the loop, right? You can see that it is created the loop, and since this side on the secondary is solidly ground, so it is connected to the ground in this case, right? And the you see in this case the x of the T2, which is zero point 0.1 per unit, is is on this side, right, on the primary side, and it is connected to the ground, so it is here, it is connected to the ground. Okay, so on this side it's connected the delta is on the ground because of the loop, right? And on the other side it is flowing in this direction. Okay, it is created the loop. So what does this J point 315? What is the J point 315 here? Okay, 0.315 is from the conversion of this, uh, x in 60 ohms into per unit. Okay, that would be, we have in this case, right, the MVA base is 100 MVA and the kV is 13.8 kV, right? So the C base, basically the C base here is 138 square kV square divided by 100. Okay, so the C base here uh, is this, right? So the X naught in per unit would be 60 divided by this guy. So this is multiplied by 100, then divided by 138 square. So it should, at least it should be the same as this one, right? And now this is the this guy here. Okay, now we don't need to do anything, right? To the motor, okay, at this number 2, it is solidly ground, and this case is delta. When there is a delta, these two is not connected. I mean, from this side of the transformer to the right side to the delta side is not connected. Okay, so there is no path for the neutral current to flow, right? So that's why you can have just the intern. I mean the reactance of the machine itself. It is what? It is 10, right? 10%. Okay, this is J point 1. This is the X naught of the machine of the motor. And since this is solidly ground, when this is solidly ground, right? There is a ground. You remember, if we have the ground, okay, the C0, right? Since there is a ground, then the current will flow. Since it is unbalanced, it will flow through the ground. So the C0 is essentially the three times of the Xn. So that's why we put three times of 0.05 pu, right? So that's why this become 15%. Okay, 0.15. Okay, this is the three times of 0.05, right? So that's why that's how you get this zero sequence. So the most problematic part of analyzing the sequence network is to deal with this zero sequence. Okay, if you can't still if you cannot still remember, or you still cannot visualize this circuit, right? I would recommend you to check the last lecture again, right? The last slides of the previous lecture. Okay, this is okay. Now you will see that we have the delta, right? If you have the delta, then there is no way for the neutral current or the I0 to flow, right? You can imagine in this way, okay? Since the delta, since this is the delta, so there is no way that the current will flow. So we have to represent this by the open circuit, okay? And the other side is solidly ground, so you just put this into the ground, okay? You will check. I recommend you to recheck this again. Okay. But the positive and the negative sequence network is rather simple. Okay, you can just still remember the positive sequence. We learned it already, right? Towards the end of the previous lecture, is that the EMF, right? The voltage source are just appear in the positive sequence network only. Okay, uh, and the when positive sequence is very simple. You just draw it like the normal power system. We started from the internal EMF, right, followed by the positive sequence. This is X double prime, so you put J 0.15, right? This is the voltage terminal at terminal voltage at bus 1, and you connect this to J.1, which is the reactance of the transformer. And you remember that the reactance of this transformer is the same for all the sequence networks, right? Meaning that X0, X1, and X2 are identical, okay? And for the line, you remember the line, we have the equal positive and negative reactance, right? So you can have just you have to convert this 20 ohms into how much per unit it is. So your X1 and X2 in PU, right? Basically, you have this 20 ohms times 100 divided by 138 square. Okay, or if you manage to find from the first problem, right, from the zero sequence, this is three times less than this guy. Okay, so if you get this 0.315, right, you can get this as 0.105, right? This is three times less. Okay, and you can see that this is three times less. And you can see for the transformer is the same, because the topology of positive and negative sequence are the same, except the negative sequence doesn't have the EMF of the generator and the motor. Okay, and the line of this, the line of X2 is 20 ohms, so it's the same as the positive reactance. So you have also the 0.105 per unit, right? And the transformer is the same in this case, right? But you can do it, or this, the problem says that the internal EMF of all the machines are at 1.05. Okay, that's why we put 1.05 on the both end, right? And then I think there should not be any problem left for you, right? The second, the negative sequence can be written in this form, right? For J.17, J.17 is here, and J.021 is here. J.21 is here, right? So we will, once we have this, right, we will try to determine the equivalence. So having this the sequence network for this particular power system, right? With this topology, we want to see, right? We want to see how much the Thevenin equivalence is. Okay, now you see that for zero sequence in this case, there is no voltage source. Okay, there's no voltage source. So in your Thevenin equivalence, there is no voltage source. You have you have just the impedance. You have purely impedance. Okay, but in this case, since there is no resistance, you have just purely reactance. Okay, the problem says that we want to find the equivalence at bus number two. Look at from bus number two, right? Um, as viewed from bus number two. I hopefully he will introduce the example will introduce different kinds of fault to bus number two. So this will be your fault location. Okay, in the future this will be the fault location. Okay, that's why we want to find the Thevenin looking from this point. Okay, the Thevenin looking from this point, you can realize from this equivalent from the circuit itself. If you stand up here at point number two, and with respect to the ground, right? Basically, you when you measure something, you measure from that point with respect to the ground. If you look from bus 2 to the ground, you don't see any effect of this bunch, because this bunch is connected to itself, right? And there is nothing to do with this bunch, right? This bunch has nothing to do with bus number 2. So this is isolated from bus number 2. You stand from here to the ground, right? If you stand from here to the ground, okay, you will see just these two in parallel. Okay, these two in parallel becomes your Z0. Okay, so your Z0 is the summation of these two, that is 0.25 per unit. Okay, now if you want to find the Thevenin equivalence for positive sequence, okay, for positive sequence, you want to see the Thevenin's equivalence. So this is rather simple. You look at these 2 points, this point, okay, and this is connected to the same voltage. So the Thevenin voltage is the same, right? It's 1.05. And once we want to find the Thevenin's impedance, right, equivalence impedance for this case between 2 and ground over here, right, what you have to do is that you just deactivate these two sources. By deactivation these two sources, you just short circuit this to the ground. When you see at this point, right, you are here and you grab these 2 points, you see that this point and this point, we have two branches, right? One branch is here, and the other branch is connected like this to the same position. So you have one branch and the two branch here. Okay, so the equivalence of the Thevenin equivalence would become, if you look from this point, right, these two branches have the same voltage drop. Okay, that's why these two branches are in parallel, right? So the total impedance you're looking from these 2 points is the point 2, right, in parallel to the series of the four. Okay, the series of these four is what? 0.15 plus zero point 0.1, 0.25, 0.25 plus zero point 0.1, 0.35, so plus another plus 1.05. So you can have what? 455, right? This is 0.455 J, okay, J 0.455, and then this is the total of these four reactances, and in parallel to this guy 0.2. So your Z1 would become, the J of the parallel of these two, right? 0.2 multiplied by 0.455 divided by 0.655, right? So after hitting the calculation, hopefully you will get this guy. Okay, you will get J 1389.13893. Okay, so you get this one. Okay, in per unit. Okay, this is the Z1. Okay, so similarly, it's follow the same. If you do, if you manage to do the positive sequence, right, the negative sequence is no problem, right? Has no problem. If you look from 2 to 0, okay, you are at these 2 points, okay, you have this branch in parallel to this branch here, okay, so this would become C2. Your C2 will be J of toy 2 1 in parallel to the sum of these four guys. So this is the point 305 plus 0.17. So you can have J of 0.475, right? J point 475, right? The parallel of these two, okay? You just have the multiplication divided by the sum. So you have this one, 0.14562, okay, which is here, okay? Remember, uh, that the positive sequence has the only network that has the voltage source attached to it is the positive sequence network. Okay, so now soon after you have this, okay, we're going to use this Thevenin equivalence for further analysis, right? Now we're going to use this example to analyze three different types of fault. So by starting this, we're gonna see the characteristics of different kinds of fault. So I'm gonna start with the single line to ground fault, right? So first thing is that we analyze the power systems under the occurrence of imbalance. In this case, this is called single line to ground. Okay, this is a single line to ground. What does it mean by single line to ground? It means that a single line or a single phase is short circuited to the ground. Okay, if you look at this topology of the system, we have A, B, C phase, and the single phase out of these three is phase A, right? The phase A just got the short circuit, right, from phase A to the ground. But of course, this is a wire a fault impedance. So the CF here is a fault. Okay, this is fault impedance. Okay, this is fault impedance. Okay, so having this picture, you see that in this case, right, since it is short circuit to the ground, right? In this case, if I don't have any CF, meaning that if I short directly to the ground without the CF, right, So the voltage drop across this point, right? There's a point A, VAG. If CF is zero, okay, my VAG is zero because it's shorted directly to the ground. So there is no voltage drop across the fault impedance. Okay, but what we can see here is that, right, since there's a short circuit to the ground only, but the phase B and phase C are not connected to the ground, so there is a polarity drop. There is a voltage drop across these two. Okay, since this is not connected to anything, right? So the current flowing out of the phase B, out of this port B, and the flowing out of port C, right? IB and IC are zero. Okay, so you can see that this is the current and voltage characteristic of single line to ground. You can see that at the in the phase domain, right? These are the phase quantities. You see that the IB and IC is zero because they are not connected to the ground. Okay, and the VAG is equal to CFIA. Okay, the voltage drop across this V to V, the port A or the phase A to the ground, which is the IA times CF, where CF is fault impedance. Okay. Now we analyzed it. We transformed the ABC sequence into a sequence network. Okay, so we draw the this picture, right? We see that from the formula that used to transform the IA, IB, IC, we transform the phase quantities into 0, 1, 2. These are the sequence quantity. We use the A inverse to multiply with the measurements in phase quantities, right? Now you see that from this picture above, okay, we have non-zero IA, but we have two zero currents, IB and IC. So we substitute IB and IC by zero, okay. So soon after having this, these are zero, okay. When you multiply, right, the matrix with the column vector, when you multiply this, you will get the second entry, right, on the right, on the left. Okay, now you see, right, that this two zero entry would cancel the multiplication of the A. Okay, you can see that these two zero zero would cancel, you know, the multiplication with A and A square. So the resultant multiplication, the result would be, I0, I1, I2 would become one third of IA. All entries are IA because what? Because the first entry only, right? The first entry of this each of this row will be multiplied by IA. Okay, because these two are zero, right? So you can see that for this kind of fault, I0, I1, and I2 is IA divided by 3. Okay, IA divided by 3. So the voltage, when we transform the voltage ABC to sequence 0, 0, 1, 2, right? What would be our observation? Okay, now this is the equation. Okay, we have VA, VB, VC, and V0, V1, V2 onto the right. So this is the A matrix, right? So now you can see that for VA, right, VA can be expressed by the multiplication of this row and the entire column here. So VA is V0 plus V1 plus V2. Okay, and the IA, since we have VA and we have IA, right, we have VA and we have IA on the right side, right? We want to express this in terms of V0, V1, V2, and we have to express this CA, which is a phase quantity, right, in terms of I0, I1, and I2. We want to transform this equation, right, this particular equation into 0, 1, 2 quantities. Okay. Now we just put these two relationships into the VI characteristics, right? What you can see here, right? you can see that the VAG is this guy on the sum of all the sequence voltages is equal to CF times the sum of all the sequence currents, right? So now you see that from earlier analysis, right? I0, I1, and I2 are the same, okay? These three are the same because I0 equal I1 equal to I2, right? Is equal to what is that? What's that? IA divided by 3, okay? So if you have this, right, the sum of these three guys, okay, you can just I0 plus I1 plus I2. We can just express this in terms of the positive sequence. If you want to improve, you express this in terms just of positive sequence. So everything is the same here. So we can replace this I0 by I1, the I2 by I1. So you have three I1s on the right. Okay. Now we can see that V0 plus V1 plus V2 is equal to 3ZF times I1. Okay. Now you can draw some conclusion based on this equation. Okay. Now you see that at the fault condition in the sequence domain for the single line to ground, okay, the first thing is that the current in all the sequence networks, right? We have three sequence networks, right? All the three currents are the same, and it is similar. It is equal to IA divided by 3, right? IA divided by 3. So the sequence current share, I mean, the sequence networks share the same current. So you can guess, now you can guess. You have three networks connected to each other, right? And these three networks share the same currents, right? So you can think of basic circuit theory, okay? What kind of connection that has the same or that has the identical current, right? This is the only connection that has this property, which is the series connection. So now you can guess, right, that the three sequence networks are connected in series because of the equal current, right? So with this property, you see that all the three sequence network, right, must be connected in series. This is before we will go to the picture. You don't need to care of so much about the picture. Everything is in the slides, right? But make sure that you can follow my explanation. Okay, and then you have V0 V1 plus V2 is equal to 3 times CF I1. Okay, now we will look to the slides. Okay, we have zero sequence, positive sequence, negative sequence in the steps. Number 3, we have a Thevenin equivalence on step number 4, right? Based on the two equations that we derived from the last slides, which are these two equations, right? You can draw this circuit number 5, as I mentioned earlier, that you have the zero sequence network, you have positive sequence, you have the negative sequence, right? And these three networks share the same currents, right? From our derivation, share the same current, meaning that these three circles are connected in series. So you can see that this the number one, the circuit, the network number 1, number 2, and number 3 are connected in series. Okay, and you still remember our definition is that the current for each of these networks are flowing out, right? And the voltage are at the terminal, okay, at the terminal. So these are the three voltages. So you have V1 from this relationship, V1 plus V2 plus V0 plus V1 plus V2. Okay, it is what? If you see from this picture, the sum of the three voltages. If I put this as a ground, okay, let's put this as a ground. V2 is, plus minus V2. This point is higher than the ground by V2, right? uh, this plus and minus here would represent, you know, uh, that this point is higher than this point by V1. So what does it mean by here? If I ask you, you know, how this point, right? How high is this point from the reference? Okay, now it would become V1 plus V2, right? At this point, with respect to the ground, okay, plus and minus, in this case is V1 plus V2, okay, V1 plus V2. Similarly, the voltage difference between these 2 points, plus here and minus here, okay, that would be V0 plus V1 plus V2, right? The voltage difference between these 2 points, meaning that how this point, how much this point is higher than this point. Okay, this is V0 plus V1 plus V2. Now this is the left side of this equation, right? This is the left side. Look at the right side of the equation. The right side of the equation is the I1 times 3 times C1, which is the voltage, right? You can see this is the Ohm's law, right? I times Z, right? This is results in the voltage. So now you can see that the current I0 is flowing through a certain resistance, as a certain resistance. Now, the I0 is the same as I1, so there is no harm that I could replace this by I1, right? And 3 times CF, it is connected as the load at this point because when the current flows through this resistor, it would create the voltage drop by plus, right, where the I mean we create the polarity plus where the point that the current is flowing into, right, uh, flowing in this port and flowing out of this port. Okay, so this would becomes I0 times 3 times CF. Okay, but the I0 is the same as I1, so there's no harm to write in this fashion. Okay, so that's why we could derive for the interconnected sequence network as in this fashion. So just remember this fact, this is my own observation. This is the way to memorize the things. You see, you can understand things. Okay, you understand how to derive this kind of circuits, right? But once you want to apply this to reality, right? You don't need to redo all the rederive everything, right? You just need some shortcut, right? So you remember, I would suggest that you should remember in this way. For the single line to ground, right, you have three sequences connected into in series, right? But of course, this is the rule of the game that the zero sequence and negative sequence do not have voltage source into it. Okay, the only sequence network which has the voltage source is a positive sequence. Okay, if you remember only this is fine. Okay, now, okay, you just remember how the topology, how these three networks are connected for different types of fault. Okay, now once you analyze this, you could find for if you know the circuit in number 5 over here, if you know this circuit, now you could analyze all the parameters. You can find voltage, you can find currents, right? Once you solve this circuit, okay, you will result in the sequence quantities. Okay, V012, I012. Okay, you from this circuit you have V012, I012. All these are in sequence quantities, but in practice, right, since we are dealing with the measurements in your real life, you measure everything's in ABC sequence. So you need to transform this set of voltage and currents back into VABC and IABC, right? You need to transform this back to the phase quantities. Okay, this is done in this step number 7, right? So after the transformation, you can see that if you know this I0, I1, I2, you know this side, you want to know IABAC, right? You just follow the formula, right? Now in this case, right, you can see that due to the fact that the I0, I1, and I2 are the same for this is the characteristics of single line to ground fault, right? This is a characteristic pertaining to single line to ground. This would make the substitution of this. If you multiply this row and this column, multiply this to this, right? You can have I0 plus a squared times I1 plus a squared I2. Sorry, AI2. Okay, since these are equal, right? Since this I0, I1, and I2 for single line to ground, then you can have the multiple, a common multiple, right, of I1. You have common multiple of I1, and you can have the factor in front, a plus a squared plus a. So if you look from the identity of this a, this is 0. Okay, I have derived this in the previous video clips already, right? That this identity is 0. So you have IB and IC to be 0. This is clear, right? If you look, why IB IC is 0? Because if you look back from to the original circuit, okay, in the original circuit, since the short circuit happens only at the phase A, while phase B and C are left to be open, right? Are still left to be open. That's why there is no current flowing from out of phase B and C. Okay, so that's why once you transform your calculation back to ABC quantities. That's why you have the 0, IB, and IC. Okay, so be cautious. Once you transform it back here, if you happen to have non-zero IB and IC to this circuit, right? To this topology, to this power system topology, there must be something wrong in your calculation. Okay, because physically there is no current flowing in phase B and C in this case, right? If you do any mistakes, you might have the non-zero IP and IC. Okay, now we transform the voltage from 0, 1, 2 to ABC, right? You do the same thing. Okay, you do the same thing for this. Okay, let me do this one example. Okay, hopefully we will finish this clip by this example. Okay, we still analyze the example 9.1, right? We introduce the fault, single line to ground fault to bus number 2, right? That's why we could use the equivalence, Thevenin equivalence that we derived from example 9.1, right? So the problem asks if there is a fault current bolted. Okay, this is the bolted. The keyword is that bolted single line to bolted means that the fault impedance is 0. Okay, if the short circuit happens at phase A to ground at bus 2, okay, the problem asks you to calculate, right, the per unit line to ground voltage at the faulted bus. Line to ground voltage meaning that the problem asks you to find VA, because the fault happened in at phase A, right? The line to ground at faulted bus. So that means that the problem asks you to find VA. Okay, so these are the 3 steps. These are the all the steps, 7 steps that you have to follow. So we analyze the power system under the occurrence of unbalanced fault, which is the bus number 2, right? and then we apply the symmetrical component with to the condition, right? We saw from last the step 3 and 4 have I mean this the step 3 and 4 have been done in the previous example already, right? But if you see this problem for the first time, you have to follow, you have to determine all these things yourself. Okay. Now you see that you have the Thevenin's network in this case, right? So you connect these three networks in the types of fault we are considering. In this case, it is single line to ground, so it's connected in this fashion, right? It is connected in series, right? And the load with the load of three times three times fault impedance. Now the problem said that the problem specified that it is a bolted fault. So this bolted means that CF is zero. So this is zero impedance would means the bare wire. So this is the single I mean the interconnected system. Okay. Now you could analyze this circuit. This is very simple, right? You would start this calculation by computing the current. It's pretty straightforward. You have just one voltage source, right? The voltage source here is already given, okay? This is the pre-fault voltage. This is the pre-fault voltage, okay? The problem says that at the pre-fault voltage, the voltage is at this much, okay? At this much, okay? Now you determine the current first. So the current would be, okay, I0 equal to I1 equal to I2, right? This is becomes your VF divided by the sum of these three, right? The sum of all these three reactants, right? Plus J.1389 plus 0.1456, right? This is the steps that you have to follow. Okay, you have to find I0, I1, and I2, right? So now you see you find the current. Soon after you know the current, right? You can determine the V0, V1, V2. You can use this equation, but if you can't remember, if you have limited memory, right, you can see directly from the figure. Okay. Since you have the I0, you still remember what I mean. If you have the I0 flowing in this direction, so there would create the voltage drop across this element by I0 times J 0.25, right? Which is this voltage is opposite sign to V0. So your V0 will be negative of your I0 times J 0.25. Okay. So similarly, you see that V1 here is Vf, right? Subtracted by the voltage drop across this reactance, okay? And then V2 is negative of this voltage drop across this, okay? So all these I0, I1, I2 are the same, so you use just the same figure, right? Or you can use you can play around with your matrix manipulation, okay? But I suppose that if you use your calculator, right? If your calculator is not modern enough, you cannot, right? You may not be able to handle the matrix in a complex form. This is dangerous, right? I don't know. This all it's up to you, okay? So that's why you can determine the V0, V1, V2 like this, okay? Now you can get the transformation. Okay, the transformation is that once you have I0, I1, and I2, if you want to find the short circuit current, in this case the short circuit current is the current flowing out of phase A to the ground, right? That is IA definitely. Okay, so the IA or the fault current or the subtransient fault current is 3 times of the I1 or I0 or I2 because all these three is the same, right? All these three sequence current are the same. So this is 3 times of your in this case this is I1, right? 3 times of the I1, so you become negative J point 5.8928, right? This is the in per unit. If you want to know how much is in real quantity, how much is it in real quantity? So you just multiply this by the base current, right? The base current here is given as, since it is in zone 2, okay? In zone 2, the base MVA is 100 MVA, and the voltage at this position is 13.8 kV, right? So your short circuit, I mean your I base here, it is 100 MVA divided by root 3 times 13.8 kV. So you have this in kiloamps, right? This is that your I base. The I base is given, right? It's here, right? So this is 100 divided by 13.8 times root divided by root 3. So you have this 4.1837 kiloamps, right? This is the 500% of this guy. So okay, 5 times higher than this guy. So this is 24.65 and the angle of negative 90 degree. Okay, so remember, right, that the base current is in real quantity. Make sure that you never and ever have the base current in complex form. This is dangerous. All right, this is dangerous. Now you have the fault current. So the problem does I did the problem ask you to determine the fault current? No, I suppose the problem asks you to determine the VA. Okay, the VA can be done, right? Because you have known the V0, V1, and V2, so you transform this back to the phase quantities, right? So you see that we have the voltage fault at phase A. Okay, you short circuit at phase A directly to the ground. So after your calculation, you shouldn't have or you should have zero VA, right? Your VA must be zero, while VB and VCs are non-zero because this is still left to be open, right? Okay, so you can see that from after the calculation, right? This is VA, V0, V1, V2, and you multiply this by the A matrix, right? You get VA, VB, and VC. So be cautious with this, that your result in this case, make sure that you have zero VA, okay? Otherwise, if you have non-zero, it is physically contradicting to the I mean to the topology of the system, right? It is in physical contradiction. Okay, I would say. Um, I think that would be more or less everything I would say, right? For single line to ground. Okay. Uh, okay, I will stop this clip by this example. We still have two more types of unsymmetrical fault to be followed in the next video clip. So have fun for today, right? And we will see you in the next video clip. Bye bye.